Hello, my name is Nolan, and I'm a research scientist at Cerebras Systems. Today, I'd like to present the Sparse maximal update parameterization, a holistic approach to sparse training dynamics. The TLDR is we introduce the Sparse maximal update parameterization, or SUPAR, which enables stable optimal hyperparameters for any model width or sparsity level. This dramatically reduces the sparse hyperparameter tuning costs and allows SUPAR to achieve superior losses, especially at scale. The motivation of this work is that when training sparse models, it is standard practice to reuse the dense hyperparameters. On the left, we show that optimal hyperparameters systematically vary with sparsity level. This means that conducting a robust sparsity study would require retuning hyperparameters for each sparsity level. This makes it prohibitive to robustly study large-scale sparse training because it's typical that a study may have, 5, 7 sparsity levels and multiple sparsity algorithms, and all of those settings would have to have a full hyperparameter search. SUPAR enables more robust sparse research. On the left, we show that SUPAR enables the same hyperparameter values to remain optimal as we vary both sparsity level and model width. In prior research that reused the dense hyperparameters, those sparse models were unfairly disadvantaged, and these studies merit reexamination. We think this is exciting because it means that published techniques for sparsity could already unlock more exciting gains than what they even published. Just expanding on the previous slide, SUPAR enables hyperparameter transfer across different levels of static sparsity. We show that the optimal learning rate is stable across sparsity levels in the top plots. In the middle plots, we show that the optimal initialization is stable across sparsity levels. And in the bottom plot, we show that if you vary both sparsity and width together, still the optimal learning rate remains stable. And just an interesting aside is that we had some dense tuned hyperparameters lying around, and we used them in this study. And those hyperparameters are actually optimal for all the sparse models in this study as well, which means technically the tuning would have been free in this study thanks to SUPAR. Next, we apply SUPAR to sparse large language model pre-training. We show that SUPAR achieves superior losses to the other parameterizations when training sparse models, and the gap between the parameterizations is growing as you increase the sparsity level. In the top, we have a 610 million parameter language model trained on 12.2 billion tokens. And as we sparsify this model, we show that SUPAR is achieving superior losses. Similarly, on the bottom, we have a 111 million parameter model trained on 1 billion tokens. And we increase both the width and the sparsity together such that the number of parameters is roughly 111 million. And we show that also in this setup, SUPAR achieves superior losses. Okay, let's get into how SUPAR works. SUPAR stabilizes sparse training dynamics. So in this paper, we show that for SP and μP, as you increase the sparsity level, the magnitude of activations throughout training will decrease. So you have a vanishing activation problem. SUPAR fixes this and allows different models of different sparsity levels to all have very similar activation magnitudes, as we show on the right. There's 3 operations that we need to control to achieve this effect. So we have the forward pass, the backward pass, and the effect of the weight update on the output activations of some layer. So the sparse maximal update parameterization controls each of these 3 operations as you change both the width of the model as well as changing the density of the model, satisfying the feature learning desiderata. If you look at this table that we have here, you can see the green highlights the SUPAR changes, and it's really just a very simple extension on top of μP. And we have a code implementation for this as well, released in the NanoGPT μP repo on a branch. The final result I'd like to leave you with is dynamic sparsity hyperparameter transfer. So in addition to static sparsity, dynamic sparsity is another exciting category of methods. And in this work, we show that for rigging the lottery, making all tickets winners, and gradual magnitude pruning on the bottom, the optimal learning rate does not remain stable with SUPAR, SP, or μP. And so this kind of opens future work to generalize SUPAR for dynamic sparse methods. And here are the references. Thank you very much.